In this video, we're going to look at something called linear approximation. It's also called linearization or local linear approximation. And it's basically another way to look at the tangent line. And if you recall, when we first looked at derivatives and tangent lines, we took a function and we graphed the function and its tangent line, and we kept zooming in on the function at the point of tangency, and we found out that eventually, if the function is differentiable at that point of tangency, that the function starts to behave like the tangent line. And as it turns out, the tangent line is actually a good approximation for the function when you're really close to the point of tangency. So we're going to start off by looking at just this generic function, some function f of x, or y equals f of x, and we'll just name the point of tangency. The x coordinate will be a, and then the y coordinate would be f of a. So there's that ordered pair, that point of tangency is a f of a. The other thing we want to look at is the slope, just the notation for the slope of this tangent line. So if I wanted to find the slope of the line that's tangent to the function f of x at a, I know I need to take the derivative, and the notation for that would be f of a. So the slope or m would be represented by f prime of a. So that's nothing new. So we've got the slope, we've got the ordered pair a f of a, and we really just want to come up with the generic form of a tangent line. And so if we use the point slope formula, y minus y1 equals m times x minus x1, and we plug in our ordered pair, so y minus f of a, the slope is f prime of a times x minus a. The x coordinate is a. And I'm going to solve for y, and I get y equals, if I add f of a to each side, I get f of a plus f prime of a times x minus a. And so really, all this is a new form of the tangent line. We used the generic ordered pair to get it. We used the point slope formula to derive it. And what we're going to call this, we're actually going to call this the linearization. And so L of x is going to be f of a plus f prime of a times x minus a. We're going to use this notation L of x, okay? And what we know is that for values of x that are very close to a, we know that L of x is approximately equal to the function f of x. So just looking at this picture, so we have our tangent line, which is now going to be named L of x. Okay? It's a linear function. It is basically the line tangent. We have f of x. At the point of tangency, both f of x and L of x are the same. As you move farther away from the point of tangency, you can see that the two functions get farther and far away from each other. But we do know that close to that point of tangency, the linearization, or the tangent line, is close to the value of the original function. Okay, and that is summarized in this paragraph below, and you can look at that a little bit later. It just restates what we derived right here. But what I want to do right now is we'll do an exploration. But before we do that exploration, I want to explain why you would use a linear approximation. And basically, the main application is to be able to model more complicated problems or complicated functions using a linear function, because linear functions are very easy to work with. So in the next video, we're going to do an exploration using this concept.